Assalamualaikum and hi student. This is a lecture video for BEKG 2443 Engineering Mathematics 2, Chapter 2, Multiple Integrals. So basically, we will try to cover these three first LOs from the first three subtopic. 2.1 Introduction to Double Integrals. So I believe you have learned how to solve for integration of single variable functions, and then this give the area under the curve. Okay, you have fx and the limits is from a to b. Now for two variables, you have this kind of integration, double integration, that give the volume under the surface in the region R. Okay, so you have fxy here, and then you can integrate respect to dx dy or dy dx as stated here. Okay, either you have fxy integrate dx dy, so you integrate dx first and then dy, or you have dy dx integrate dy first and then after that you integrate respect to x. Four properties of double integrals. Okay, for example, you have two function with two variables and they are continuous, and then we have constant multiple, so you can have c as constant. Okay, and then you can integrate, do double integration first, multiply by c. And then for sum and difference, if you have sum and difference between these two functions, you can split them. Okay, solve the double integration for the first function first, plus or minus with the second integration. And then domination, if you have double integration of fxy and this is greater than 0, if your function itself is greater than 0. And second one, for domination, if double integration of fxy is greater than double integration of gxy, meaning that your fxy is greater than your gxy. And the last one, we have additivity. Okay, if you have double integration of fxy in region R, where R is union of region R1 and R2, and R1 must not intercept with R2. So you can solve this double integration by split the R1 and R2 region. Okay, let's do these two examples. For A, we have double integration of 0, 3, 0, 2, 4xy plus 3y dy dx. Okay, 0, 3, do the integration, do this integration first. Okay, dy first. So you have the integration for xy respect to y, you have 4x y square divided by 2 plus 3y square over 2, and the limit for y is 0 to dx. For this one, you have 0, 3, 4 divided by 2 is 2, then x y square, substitute the value for y is 2 square plus 3 over 2 square dx. Okay, and then you have 0, 3, you have 4, 8 x plus 3 over 2 multiplied by 4 is 6 dx. Okay, and then solve for dx, integration of x. So you have 8x squared over 2 plus 6x. The limit is from 0 to 3, and this is 4. Substitute the value of x, which is 3 square plus 6 multiplied by 3, and this is equal to 36 plus 18. 36 plus 18 is equal to 54. For example B, we have to solve for 0, 2, 0, 3, 4xy plus 3y dx dy. Okay, for the second example, we need to solve for x first, integration of x first. So this is equal to 0 to, then integrate 4xy respect to x is equal to 4yx square over 2 plus 3xy. Okay, the limit is from 0 to 3 for x limit. Then this is 0 to, substitute x equal to 3, so you have 4y multiplied by 9 over 2 plus 3 multiplied by 3 is 9, so we have 9y here dy. And for this one, we have to do the integration of 9 multiplied by 2 is 18y plus 9y dy. And 18 plus 9 is equal to 27y dy. Integration, using the properties, you can put out the 22, so you have to do the integration for y. So y, integration for y is y square over 2, from 0 to 2. Substitute the limit, you have 2 square multiplied by 2 square 4 divided by 2 is equal to 2. 27 multiplied by 2 is 54. Subtopic 2.2, double integrals over rectangles. Okay, so we have theorem 2.1 for Fubini's theorem. Okay, it states that if fxy is continuous throughout the rectangular region R, x is from A to B and C is from and y is from C and D. Okay, then double integration of the function fxy dx is equal to, okay, you can either have dx dy or dy dx with correct limit of x and y. So this explains why the previous examples have the same value, which is 54. Okay, for this example, we need to calculate double integration of fxy dA for our fxy is equal to 2y minus 6xy. And the region, the rectangular region R, is for x from 0 to 2 and y from 0 to 1. So if we sketch our region, we have x from 0 to 2 and y from 0 to 1. So here is our region. So to calculate for this one, okay, you can have double integration fxy, which is 2y minus 6xy. Okay, you can do the integration for dx dy, okay, and then put the limit for x. The limit for x is 0 to first, and then followed by limit for y 0 1. Okay, so this is A. Or you can do the double integration for, okay, double integration, you have 2y minus 6xy dy dx, which is the limit is 0 to 1 and 0 to 2. Okay, both answer will be the same. Okay, let's try for A. The last answer is minus 4. Okay, so you can try for B, solving for B, and you should get 0 to 0 1 2y minus 6xy dy dx equal to minus 4 as well. Second example, when you have this double integration y sine xy dA where r is equal to 1 to cross 0 pi. Okay, so this is written as double integral y sine xy. Okay, if you want, so dx, for dx dy, this is the limit for x, so 1 2, and this is limit for y 0 pi. Okay, so solve for dx dy, you have 0 pi. Okay, to solve for y sine xy respect to x, Okay, you need to use the substitution. So we let u equal to x, y. So du is equal to y dx. Okay. Differentiate x, y respect to x. So you have y dx. And then for the substitution, when x equal to 1, so your u is equal to y. And then for x equal to 2, your u is 2y. Okay, and then y dx is equal to your du. And then sin xy is equal to sin u. So you have sin u du dx. So this is how we do the integration by substitution. So 0 pi integrate sin u, we have negative cos u. And the limit is y to 2y. This is dy. So substitute the value of u. So you have negative cos 2y minus plus cos y dy. Okay. From here, we integrate this fy with respect to y. So integrate negative cos 2y, we have negative sin 2y divided by differentiation of this 2y is 2 plus integrate cos y is sin y. Then we have the limit for y is 0 to pi. So for this one, substitute the value, we have negative sin 2 pi divided by 2 plus sin pi minus we have plus sin 0 over 2 minus sin 0. Okay, since sin 2 pi is equal to 0, sin pi is equal to 0, sin 0 is 0, and this well is 0. So we have this equal to 0. Moving to the third subtopics, double integrals over non-rectangular regions. Okay, theorem 2.2, Fubini's theorem for non-rectangular region. Let's say we have a function of two variables, okay, on a region R. First, if R is defined by A to B for X, okay, X is from A to B, and we have Y, okay, Y, limit of Y, the lower limit is G1, function G1, and then the upper limit is function G2, okay, with G1 and G2 continuous on AB, okay, on AB here, then double integration of fx y in R, region R is equal to, okay, you can have this double integration G1, G2 respect to y first, and then do the second integration respect to x for limit A to B. Or, and if R is defined by this, your x is bounded by h1 and h2, function h1 and h2. The limit for y is CD, fixed number, with h1, h2 continuous at CD. Okay, and you can have this second expression of double integrals. Okay, CD have h1, h2 for limit x, then this one is for limit y, and you will find out that these two will give you the same values as long as you refer to the same region. We have definition 2.1. Okay, we classify this into two type of region. Type 1 region, bounded on the left and right by the vertical lines x equal to A and x equal to B. It's bounded below and above by continuous. This is the curve. This is the two curve G1 and G2. So this is your region R. Okay, R1, let's say. When you do the double integration, you will do the double integration R f x y, you have dy dx. And for type 2 region, okay, we have this region bounded by this second region bounded by y equal to CD. So this is C, this is D, and the vertical we have x equal to H1 and H2. So for this one, if you solve for double integral, you have to solve for dx first, followed by dy. This is the difference between the first region and the second region, the second type of region. To the examples, okay, for we need to solve for A and B. So as we can see here, A 0 to x square to 2x, okay, 3x plus 1, this is our fxy, and this is the limit for y dx. Okay, so we have fixed limit for x and y. We have the curve x square and 2x. Okay, so this is type 1 region. So solve for this one, 16 over 3. For B, we have to do the integration, double integration for 3x plus 1. The limit is from 0 to 4 for y limit, and then for x limit, we have function y equal to y is over 2 and square root of y. So this is type 2 region. Okay, and then if we solve for this one, the last answer is 16 over 3. So you see the last answer for type 1 and type 2 is the same, because we consider the same region, just change the order of integration. After this, we will look at how we find the limit and then reverse the order of the integration. There are 4 steps in finding the limits of integration. Okay, the first step is to sketch the region of integration and label the bounding curve. Okay, sketch the region and label it. Okay, because in step 2, we will try to find the y limit from the region you sketch in step 1. So basically, y limits we find out with using the vertical lines. Okay, using the vertical lines, and we find the y limit. This is for type 1 region. Okay, mark the y values where the vertical line enters and leave. Okay, the third step, once we have our y limit, we need to find what is x limit. X limit is a fixed number. Okay, so you need to solve simultaneous equation to find what is the value of x. And then the fourth step is to write the double integrals and solve the problem. Okay, to further understanding on how to sketch, how to find the limits. Okay, the 4 steps before I explained before. So we have this example. Find the volume of the solid that lies under paraboloid z equal to x square plus y square. So this is your fxy. Okay, and above the region D in the xy plane, bounded by the line y equal to 2x and the parabola y equal to x square. Okay, so from these 2 equations, from this line and the parabola, you need to sketch the region. So you have xy plane. So this is your y and this is your x. The first line, you have y equal to 2x. So you have just straight line, this straight line, and this is y equal to 2x. First steps. Okay, and then for the second, the parabola y equal to x square. So y equal to x square is this one. So this is parabola y equal to 2x. And then see where is the region that bounded by these two curve. Okay, so obviously it is right here. Okay, so this is the region. Okay, the first steps. Second steps is to find the limit. Okay, y limit. Find the y limit first. Okay, use the vertical line. So vertical line is from here. So it goes from here. It enters from here. So this is the line. The line of y equal to 2x. So y equal to 2x is your lower limit. Lower limit y. Okay. And then it goes into the region and then leave the region from this line, which is y, this is y equal to x square. So y equal to 2x is the upper limit of y. So now we have the limit of y. The third step is to find the limit for x. So for x, so this is x equal to 0. So x equal to 0 is the lower limit. And for the upper limit, okay, so for upper limit of x is right here. So you need to find what is x here. So since this is intersection between y equal to 2x and y equal to x square, so you need to solve this two simultaneously. So x square is equal to 2x. So x square minus 2x equal to 0. So x minus 2 equal to 0. So you have x equal to 0, which is this point, and x equal to 2. So this point is equal to x equal to 2. So the upper limit for x is equal to 2. So this is upper limit of x. Okay, and the last step is to write the integrals and solve it. So to write the integrals, you have double integrals, and this is your fxy. Fxy is equal to x square plus y square. Okay, so in second step, you find the limit for y. So you need to solve for dy first, and then followed by dx. So limit for y is x square. X square is lower limit, and upper limit is 2x. Okay, for put in your x limit. Lower limit x is 0, upper limit is 2. Now you can solve for double integrals. The last answer will be 216 over 35. Second example, evaluate, this is your fxy, which is equal to x plus 2y, where D is the region bounded by the parabolas y equal to 2x square plus 2x square and y equal to 1 plus x square. So first sketch the region. Okay, so we have x, y plane again. So this is y, this is x. So y equal to 2x square. Y equal to 2x square is this one. Okay, so this is y equal to 2x square. And then y equal to 1 plus x square, meaning that you have intercept y equal to 1. So y equal to x square is something like this. And the intercept here is 1. So the second curve here is y equal to 1 plus x square. So the region D is here. So label the region D. Okay, so this is the region. And then moving to the second steps. Okay, use the vertical line. So you enter the region from here. So this is your lower limit of y. So lower limit of y is y equal to 2x square. Okay, lower limit. And for the upper limit, it leaves the region here at curve y equal to 1 plus x square. So this is how you determine the y limit. And the third steps is to find the x limit. Okay, x limit is from here to here. So find what is the value for x. Intersection kan? Right. So you have y equal to 2x square equal to 1 plus x square. So you have x square minus 1 equal to 0. So x plus 1, x minus 1 equal to 0. So you have x1 equal to negative 1, x2 equal to 1. Meaning that you have negative 1 here and 1 here. So for x limit, x equal to negative 1 is the lower limit. Okay, from here. And then x equal to 1 is the upper limit. Now you have all the limits. You can moving to the fourth step, the last steps, to write the double integrals. Okay, so you have x plus 2y. In second steps, you have y limit. So you write your dy first, followed by dx. Put in your y limit and x limit. So lower limit is 1 over x square. The upper limit is, this is upper limit. 1 plus x square. Your lower limit is 2x square. Lower limit is negative 1. Your upper limit is 1. Okay. So try to solve for this integration, double integration. And make sure the last answer is equal to 32 over 5. Next, reversing the order of integration, or I might say this to find the limit for type 2 region. Okay, before this we considered the type 1 region, dy dx. So this one is for dx dy. Okay, step 1, sketch the region. The same things you need to do. The second step is to find x limit. Instead of y limits, you find what is x limit. Okay, use the horizontal line. And then the third step, find the y limits, the fixed value of y and the fixed value of lower limit y and upper limit y. And the last step is the same, write the double integrals and solve it. For this example, you need to calculate integration 0 to 4x, y, we have x over 2 to 1, for fxy equal to exponent y square. For this case, you cannot solve this with y first, followed by x. Because exponent y square cannot be integrated respect to y. It's difficult for you. Okay, so what you can do is to reverse the order, to change the order. Instead of solving for dy dx, you solve for dx dy. So to reverse the order, you need to sketch the region. The first steps. Okay, so you have y, x. Okay, so limit for y is x over 2. Lower limit for y is x over 2. Is a line. Y equal to x over 2. So this is the line. Y is equal to x over 2. And the upper limit for y is equal to 1. This is the upper limit because this is y equal to 1. So this is the region R. Okay, region R. And x limit is from 0 to 2. Okay, if you solve this, y, substitute y equal to 1. So your x is equal to 2. So this is the limit. The second step is to find what is your x limit. Okay, x limit since you have type 2. So for x limit, use the horizontal line. So it's enter from here, which is x equal to 0. This is lower limit of x. And then it leave the region from this line, which is x equal to 2y. Okay, so x equal to y is the upper limit for x. Okay, instead of using the vertical line, now we use the horizontal line. And the third step is to find the limit for y. Lower limit for y is right here. It is equal to 0. Lower limit. And upper limit for y is y equal to 1. This is upper limit. Okay, settle with step 3. Moving to the step 4. Double integration. When we reverse the order will be, okay, we don't change the fxy. So fxy is remain as exponent y square. Do not change the fxy. Do not change the function. We just change the order. dx, dy. So x limit is from 0 to 2y. And y limit is from 0 to 1. Okay, so then we can solve for this double integral. So this is equal to 0, 1. Okay. Okay, step 4. Okay. This is 0, 1 integration 0, 1. So integrate exponent y square respect to x. We have x exponent y square 0 to 2y dy. Okay, we have 0, 1. Substitute x with 2y. So you have 2y exponent y square dy. Okay. To solve for this, you need to use the substitution. Okay, so substitution, we let y square equal to u. So u is equal to y square. So du is equal to 2y dy. Okay, so this one, substitute it. The limit, substitute the limit as well. So when y equal to 0, u is equal to 0. When y equal to 1, u is equal to 1. And 2y dy is equal to your du. Okay, so exponent y square becomes exponent u du. 2y dy is du. So integrate exponent u, you have exponent u, divide by 1, so exponent u. So this is equal to exponent 1 minus exponent 0, and as we know, exponent 0 is equal to 1. So this is one of the reasons why we need to reverse the order of integration. For second example, we have 3 double integrals here. Okay, so we need to sketch the region of integration, write an equivalent double integral with the order of integration reverse, and evaluate the integrals. So let's see the first question for A. Okay, A first sketch. So when you sketch this, you have x, y. Okay. 4 minus 2x. Okay, y equal to 4 minus 2x. When y equal to 0, x is equal to 2. And when x equal to 0, y is equal to 4. So this is 4. So this is the line. So y equal to 4 minus 2x. And then limit for y is, lower limit for y is 2. Okay, so this is 2. Y equal to 2. And this is x equal to 1. So the region is here. Okay. So this is the region. And then to reverse the order, second steps, we need to find what is the x limit for dy dx, because this is type 1 region. So we need to reverse to type 2 region. Okay, for type 2 region, we use the vertical line. So vertical line from here, so x limit is from 0, and then you have leave the region here. So this is, when you write this in terms of x, you have x equal to 2 minus y over 2. So this is the upper limit of x. So for x, we have 2 minus y over 2. Limit for x. Third steps for y limit. Y limit, obviously, it is from 2 to 0.4. So the y limit is from 2 to 4. Okay. And the last steps, you can write this as 2, 4, 0, 2 minus y over 2, y dx dy. Try to solve for this one. The last answer is equal to 8 over 3. Then for B, since this is type 2, you have dx dy. So you need to reverse the order, becomes types 1. Okay. So for B, the first steps, you have y and x. Okay. So the x limit is equal to y. So x equal to y is equal to this line. This is xy. And x equal to y square is this parabola. X equal to square root y. So this is the region. Okay. So the region. So for second steps, reverse the order. So from type 2 to type 1, we use vertical line. So y limit. For y limit. Okay. For y limit, the lower limit is y equal to x square. Okay, so equal to x square, and the upper limit is this one. Okay, so y is equal to x. And the third step, x limit. Okay, find what is this value for x. So the lower limit of x is obviously 0, and the upper limit for x is equal to 1. When you solve this simultaneously, okay, square root y equal to y, okay, you get 1. And the fourth steps, double integral is written as 0, 1 x square to x dy dx. And solve this, you get 1 over 6. And last example C. Okay, you have this limit of x and y. This is limit for x, this is limit for y. So you have dx dy, this is the type 2 region. Then you need to reverse it to be a type 1 region. So for this one, you have y, you have x. You have x equal to, for the limit, you have this one. X is equal to square root 1 minus y square. Okay, so you see this is actually x equal to 1 minus y square, and x square plus y square equal to 1. So it's actually a circle with radius 1. So you can draw the circle with radius 1. Okay, for x limit. And then for y limit, y is from 0 to 1. Okay, so y from 0 to 1. So this is the region. Okay, this one is x equal to positive 1 minus y square. And this negative part is for x equal to negative 1 minus y square. Okay, from negative to positive. Okay, negative part to positive part. So you have the semicircle. So second steps, you need to find the, you need to use the vertical, the vertical line, because you want to find the region 1, first region. So the vertical line for y, limit y is from 0. And the upper limit is this line. Okay, so you have this x, so your y, so x square is equal to 1 minus y square. So y is equal to square root 1 minus x square. So the upper limit is square root 1 minus x square. The third step, x limit. X limit is from negative 1 to 1. So negative 1 to 1, and you can solve for the fourth steps. Double integral, you have negative 1 to 1, you have 0 to square root 1 minus x square. And then you have your fxy, which is equal to 3y. And you have dy dx. Check your last answer. It's supposed to be equal to 2. Okay, definition 2.2 give the definition of area in double integrals. Okay, the area of a closed region bounded by region R is equal to 1 dA. You can have A equal to double integration dx dy or dy dx. So basically we have two examples. Okay, we try to solve for the first example first. Okay, use a double integral to find the area of the region R enclosed by the parabola y equal to x square and the line y equal to x in the first quadrant. For the first steps, we have to sketch. Okay, to sketch for y-x plane. Okay, the parabola y equal to x square. So this is y equal to x square. And then y equal to x is a line. This is the line for y equal to x. And this is your region. Okay, with intercept here we have 1 and 1. First quadrant means this quadrant. This is second quadrant. Okay, first quadrant you just have this one. So for the second steps, okay, you can solve using dx dy or dy dx. Okay, whatever you want to use. So for this one, I want to find what is y limit. So y limit, so I enter this from here, from x square, and leave at x. So this is my y limit. The third steps is to find the x limit, and obviously my x limit is from 0 to 1. The fourth steps is to find the area. The area is double integral. So since I have x square over x square to x, so this will be my dy. And then I have 0 to 1. This is dx. Now my fxy is equal to 1. Okay, so for area equal to 1 over 6. So the area for this region is equal to 1 over 6. Just need to substitute fxy equal to 1 for area. We have to find the area of the region R enclosed by parabola y equal to x square and the line y equal to x plus 2. So as usual, we start with sketching the region. So y equal to x square is this one. And y equal to x plus 2. When y equal to 0, x is equal to, when x equal to 0, y is equal to 2. So it intercept at 2. Okay, it's a straight line, intercept at y equal to 2. So this is 2. And this is the bounded region. This is our R. Okay. From here, you know that this is 1, and then you can have this as dy dx or dx dy. Okay, so let's say I want to use dy dx. This is my lower limit and this is my upper limit. So my lower limit is x squared. My upper limit is x plus 2. My x limit is -1 to 2. Okay, for area. So this is the area equal to 9/2. Okay, that's all for this video. For the next video, we will continue with polar coordinate and introduction to triple integral. Thank you.